This is Professor Kuehn. In my last lecture, I talked about how Archimedes Principle, the fact that a submerged body has a buoyant force acting on it that is equal to the weight of the fluid that it displaces. I talked about how Archimedes Principle can be derived from the concept of hydrostatic pressure. That was one of Pascal's great insights, is that when you have a fluid, the pressure varies with depth. And the fact that the pressure on the top of a submerged body causes a downward force, the pressure on the bottom of a submerged body causes an upward force, and that this upward force exceeds the downward force, so that excess upward force is what we call buoyancy, and we showed that the buoyant force is equal to the weight of the displaced fluid. That's what we did in our last lecture. So we're talking about chapter 15 in A Student's Guide to the Great Physics texts. We're right around page 190, 191. The content of the last lecture was really on page 190. What I want to do now is focus on page 191, where Pascal explains why it is then that some bodies sink and other bodies float. So the question that we're asking is, whoops, let me go back for a moment. The question is, why do some bodies sink while others float? That's the basic question that's being asked. And I'll tell you what the answer is. What Pascal mentions is that if the weight, and I'll explain how we arrive at this in a moment, but I'll just state what the answer is. If the weight of the body exceeds the buoyant force, then the body sinks. While if the weight, again, of the body is less than the buoyant force, then the body floats or ascends through the fluid. And finally, if the weight of the body equals the buoyant force, then the body remains stationary. I would say, yeah, stationary inside of the fluid. I guess technically speaking, we would say there's no acceleration of the body. Okay, so it stays put. So that is the answer. So how can we think about this? So let me do this by way of a few examples. So example 1. So let's imagine that we have a copper block. A copper block that is submerged. Oops. A copper block that is submerged. So let me draw some water here. And again, this could be any kind of fluid that you wish. We have this copper object that is submerged. And this copper object feels forces acting on it. One that we've been talking about is this buoyant force. The buoyant force acts upward. Again, this is because there's an unbalance in the force that the pressure exerts on the bottom and on the top. And then also, because this copper block has weight, there is a force of gravity pulling on it, or its weight. Okay, so what is the buoyant force? So I've drawn this in a suggestive way that the weight exceeds the buoyant force, and that's why this object shrinks. So let me explain why this is. So remember the formula for the buoyant force, it's equal to the weight of the displaced water. The weight of the displaced fluid. That is Archimedes' principle. So what is the weight of the displaced fluid? Well, it's just the mass of the fluid that would occupy this space times g. So the mass of the fluid times g. And what is the mass of the fluid? Well, it's the density of the fluid times the volume of this copper block times g. All right, so this right here would be the mass of the displaced fluid. Okay, what about the weight of the copper block itself? That's the weight of the copper block, or copper cylinder, I guess is the way I've drawn it. And that would be the mass of the copper block times g. And what is that? Well, that would be the density of the copper times the volume of the copper times g. And you can see right away that these two expressions, the buoyant force and the weight, look an awful lot alike. They both got this g. They've both got the volume of the copper, but where they differ is this one has the density of the fluid, this one has the density of the copper. And so since the density of the copper is equal to 9 times the density of the fluid, water, the specific gravity of copper is 9, that means that the weight is greater than the buoyant force, and hence the copper block sinks. Okay, what about example 2? What about if so copper block submerged, this sinks. What about a wooden block that's submerged? Well, you can do the same kind of thing. So I'll imagine we have, again, some water. Let's make it a nice wooden cylinder looking the same as the copper, but now this is made of wood, not of copper. So here, well, it's got, once again, a buoyant force acting up on it. And let's just make this to be the exact same volume as this one had been. Because it's the same volume, it's going to displace the same amount of liquid, and so the buoyant force is going to be the same. But the weight of the wood is going to be smaller. Okay, so insofar as this buoyant force exceeds the weight, it's going to float. So once again, the buoyant force acting on this is going to be the density of the fluid that's displaced times the volume of this wood times g. And the weight of the wood is the density of the wood times the volume of the wood times g. And notice now that the buoyant force is going to be greater than the weight. Why? Because you have a factor of g in both cases, a factor of the volume of wood in both cases, but here the density of the fluid is greater than the density of wood, and so the buoyant force is greater than the weight, and hence it floats. Now here's an interesting question. We could ask ourselves, if you put, so what's going to happen is the buoyant force is bigger, it's going to float up toward the top, and it's going to kind of come out of the top of the water, but how much of the wood is going to be sticking out of the top of the water? So let me ask that question. How much wood is beneath the surface of the water when the wood is floating on the surface? How should we think about this? Well, let me draw the surface of the water. Draw a few cases, so let me draw it like this. Okay. Now, let's suppose that we were to start out with this wooden block. We were to push it down so it's submerged underneath the water. And as we saw a moment ago, when you do that, the buoyant force is larger than the weight. And so the net upward force causes it to move upward. But let's suppose instead that we have this copper block, we kind of hold it up out of the water a little bit too high like this. So we grab it, we pull it up out of the water. Well, the weight is still the same, right? The wood still weighs the same amount, but now it's only displacing a little bit of water, and the weight of that displaced water is going to be very small, so the buoyant force is going to be very small. And so what's going to happen, whereas in this case, it's going to want to accelerate upward. In this case, because the weight is bigger than the buoyant force, it's going to want to accelerate downward. It's going to want to fall deeper into the water. But if we have it at just the right depth, it's going to settle to just the right depth so that the weight is exactly canceled by the buoyant force. In other words, it's going to settle to a depth where the amount of water displaced is such that the weight of that displaced water causes a buoyant force which is exactly equal to the weight of the object itself. So in this case, the buoyant force is greater than the weight. That means it's too low, too much submerged, and it's going to pop upward. In this case, the buoyant force is less than the weight, and so it's too little submerged, and so it falls downward. And in this case, the buoyant force is exactly equal to the weight, and that means that it's going to sit at rest. And this condition that the buoyant force equals the weight is going to provide us with a way of figuring out exactly what fraction of this is submerged. And you might remember in a homework problem we did at the beginning of the semester, we found that the fraction of this that is submerged is going to be, excuse me, it's going to be equal to the ratio of the density of the wood to the density of the water. So you might want to look back at that problem that we did earlier in the semester using Archimedes' principle. Before I finish, let me say one other thing. If we were to push this down too deep, and then release it, I said it's going to pop upward, but what's typically going to happen is it's going to overshoot a little bit, go too high, then back too low, too high, too low, and eventually settle to the correct height. So if we were to plot the position of this wooden block as a function of time, so this one might call the y position of the height. This is the position above or below its equilibrium position. And by equilibrium position, I mean the position such that the buoyant force equals the weight. And this might be time. If we started out too low, it's going to pop upward, but then it's going to overshoot and come back down and go like this and kind of oscillate, and then eventually arrive at its equilibrium position. So it's sort of the amplitude of this oscillation is going to decrease over time until it settles at its equilibrium position. And the number of times it bobs up and down is going to depend on the viscosity of the fluid. So the time to settle is dictated by the fluid viscosity. The more viscous the fluid is, the more rapidly it is going to settle down to its equilibrium position. And I think with that, I will end this lecture.